Hello, everyone. Welcome to Homework 4 Part 1 Bootcamp. Today, we will be trying to discuss some tips and tricks that help you to implement Homework 4 Part 1 faster and more efficient. All right. First of all, let's begin with an overview of today's bootcamp. We will be covering two main parts. So, the first one is mask self attention part, which works as a separate PI file that you have to implement and submit in AutoLab, and also the part related to language modeling, which should be implemented as a Jupyter notebook, and altogether it's submitted to AutoLab. Um, all right, let's begin with the first part with the masked self attention. Before we dive into the mask self attention, which is a specific subtype of attention, let's zoom out and see that in conventional transformer, actually attention is used in multiple parts. So in the encoder part, we see that they're using multi-hat attention. And then in the decoder part, there are two types of attention. There is masked multi-hat attention and also cross attention. There are different types of attention, but essentially all of them, they have the same, very similar underlying mechanism that we will ask you to implement in homework for part 1 from scratch, and this will help you to understand how it actually works in the original transformer and any follow-up models. To think about different types of attention, so there is type number one, there is self-attention, when we take a single sequence and we analyze the relationship of different words like tokens within a single sequence. There is masked self-attention, when we take exactly the same sequence, but we basically mask some of the tokens and not allow the model to operate and use those for different tasks. There are different ways to implement this mask. It would be causal or look ahead mask. If we take a sentence and we basically mask all of the words that comes after or in the future, so the model won't see the basically future words. There is a pattern mask, there is a localized mask, different types of masks. In homework for part 1, we will be asking to implement masked self-attention with a causal look-ahead mask, which means we will ask to implement a self-attention that will analyze the relationship within a single sequence, and it will not have an access to future words or future tokens. Other types of attention includes cross attention. As you remember in the original transformer, we have encoder and decoder part, and so we can combine them using a cross attention, which will basically learn which parts of the input sequence are the most important to the output. So it's like it's cross attention. And also there is multi-head attention. If we want to pay attention not just like to one aspect of specific tokens, but to multiple, we will be using multi-head attention. All right, so as I said, so we in the homework for part 1, we will be focusing on masked self-attention with a causal mask. Um, and just as a motivation, how would it actually be implemented? So imagine this is in the image number 1. In this example, the model can actually see all the future data, and will assign the weights to all of the basically tokens in the sentence. But sometimes we don't want it. Like if we want to be working with the future sentences and we don't want the model to see the future data, we want to do something with those future tokens to make sure the model doesn't pay attention to them at all. And there are multiple ways to think about like what can we do? Like can we mask them? Can we remove them? Can we what should we do with them? And the original paper, attention is all you need, they come up with really interesting approach how to actually achieve this goal. All right, let's see step by step how we can achieve that. So, step number one is very easy, as you encountered in other attention calculations. We just get queries, keys, and values. We can learn them, we can assign them. We just got those matrices to operate with next. Step number two, we multiply our queries by keys and get this value. So this is our basic weights, raw attention weights, which will say like how much attention, basically would say something about the relationship between the words in the sequence, how much they are associated with. But as you can see in these calculations, all the words basically, the model actually even say like it can pay attention to future words as well. And we don't want this behavior. We want to come up with some idea how the weights of the future words would be irrelevant. And the way to do that, we can come up with a mask. So imagine we create a brand new matrix, a mask, that will assign large positive or large negative values to all the values to all the weights in the matrix that comes after the actual word. So basically, all the future words, all the weights for the future words become large positive or negative value. And this is a very interesting property to have. And so what we'll do is, like, we have the original weights and we have this mask, and we can just add them. So we can just overlay. So we have the original weights, we add a mask, and we receive a new output. And there are multiple ways we can do multiply or add. In this example, in this homework, we will use add for numerical stability. And so essentially, in the end, we'll receive this new matrix where the weights for all the future tokens will be assigned, will get this super large value. And why we do this, so like as you remember, the next step in attention is softmax. So if we pass this, the previous matrix to a softmax, the values, the future tokens will become zeros, which is the values for the weights will become zero. What this means is that when the model will decide, like, oh, should I, for this particular word, how much should I pay attention to, like from a particular previous word, those that are zeros, the model will not be using them at all. And so we achieve our goal, basically. Yeah. And once we got this, we do a final step when we multiply the result by the values, and we receive our final matrix. And yeah, and so we achieved our goal. And in this example, by implementing mass self-attention, we learn and we show a model that the weights of the future tokens do not matter. Just pay attention to whatever comes past and present. And we provide a lot of instructions in the write-up. So in write-up, you have to implement the forward part and the backward part of this, the entire mechanism. So you would see, like on the pages, there is a forward equations, which basically similar to what we discussed before, and also there are backward equations. And important to say that mask doesn't influence the calculations of the backward, because simply what we do, we just add something like some constant to attention weights. That's why your backward calculations remain the same. All right, and yeah, if you have any additional questions, please post in Piazza, visit office hours, and also plenty of extra materials on the internet, because this topic is really interesting, and many people trying to write some tutorials explaining how to work on this. And also in lecture 19, you can see additional information. All right, thank you so much. Moving on to the next part.
So now we'll talk about the language modeling component of this homework. Language modeling is basically the task of predicting the next token given the previous few tokens. So at every time step, a language model will give you the probability distribution over the vocabulary from which you can draw a next token. So you can imagine that a language model can be used for generating sequences. However, if you are already given a sequence, then a language model can also be used to measure the probability of that sequence of tokens occurring. So if you remember from the lecture, the probability of a sequence can be broken down into the product of individual probabilities at each time step using the Bayes rule. So the probability at any time step would be the probability of the next token, the additional probability of the next token, given the previous tokens that have already occurred in the sequence. So we'll be using this kind of breakdown for this process of calculating probabilities of an entire sequence. We also implement SOS to the beginning of the sequence and the EOS token to the end of the sequence to mark the completeness of a sequence. The next question is that how do we actually represent tokens? So tokens are basically discrete, right? They are indexes in a vocabulary. So one way to represent them would be to represent them as a one-hot vector, but this is practically infeasible because vocabularies are typically large. So if your vocabulary is of size 10,000, every token's representation would be a sparse vector of size 10,000 with just one element being one. That is very wasteful, right? So instead, what we use is a lower dimensional uh, vector which is called embedding. So you will be using PyTorch's embedding layer to implement this. So embedding is basically a matrix, a projection matrix that takes an index in the vocabulary and converts it into a lower dimensional vector. So you can think of it as a matrix which has one row or one column for the embedding of each token. The row or column thing depends upon your implementation. So if your vocabulary is of size 10,000 and your embedding size is 512, so the matrix would be 10,000 cross 512 or 512 cross 10,000. So once we have the embeddings for individual tokens in the sequence, so consider our sequences SOS, FOUR, space, S, and so on and so forth. So you first get the embeddings of each token in the sequence, then you pass this entire sequence through your language model. So here we are considering the language model to be an LSTM. Then at every time step, you will get probability distribution over the vocabulary. However, at every time step, you know the actual next token, right? That, for example, at t equals 0, when the input was SOS, you know that the actual next token is F. At t equals 1, when the input was F, you know that the actual token was O. So in the probability distribution, you pick up the probability of the actual next token, and you do this for every time step. Then eventually you multiply all these probabilities to give you the final probability of the entire sequence. Now in practice, what happens is that when you keep multiplying probabilities, they will keep shrinking, right? So we do instead is we do log of the probability of the sequence so that you can take log of the individual probabilities and add them all together. Uh, in pseudocode, it looks like this. So you iterate over time steps. At every time step, you convert the token ti. At every time step I, you convert the token ti. T is the sequence here into its embedding e. You pass the embedding and the hidden state which is coming from the previous time steps into your language model, which can be RR and LSTM. Then you get the output probability distribution y. From that y, you pick up the probability of the actual next token, which is ti plus 1, and you take its log. And then you keep adding all these log probabilities together till you reach the end of the sequence. And finally, what you get is the log probability of the entire sequence. Now we use this kind of log probability of the sequence concept to also train a model. So the idea is that you want to train a model. The idea is that you have a set of sequences in your training data. You want to train a language model that will maximize the probability of this entire data set. So it's called maximum likelihood estimation because we are training parameters such that they maximize the likelihood of the training data. So if your training data has n sequences, then you want to basically maximize the sum of the log probabilities of the sequences. And if you talk about it in loss terms, you want to minimize the negative log probabilities of the sequences or the sum of the negative log probabilities of the sequences. So that is what the loss definition is on this slide. And as discussed earlier, the log probability of one sequence is basically the sum of the log probabilities at individual time steps. Now, how you will actually be implementing this, let's understand that with the help of an example. So you are given in this homework, you will be given a bunch of articles. So you basically have a huge corpus of text. We'll discuss the data set in the coming slides. But and you will be breaking this corpus into individual training sequences. So consider that you are training a character level language model, even though this homework is a word level language model. Let's, for this example, consider that you are training a character level language model and the entire training text that is given to you is 4 space core space and space 7 years ago. You decide to take training sequences of length 5. So your first training sequence would be FOUR space. Now the targets for it would be the actual next tokens. So at time step 0, the target would be O, then U, R space and S. The final S is actually in the next sequence, but it is definitely the target for the last token of the current sequence. So once you have the inputs and targets, you can basically pass the inputs to the embedding layer. You get input embeddings, and you pass them through your language model to finally get the probability distribution over the vocabulary at every time step. Then you can take probabilities of the actual next tokens, which are the targets, take their log and sum them up, or take the negative log and sum them up to get the final negative log likelihood loss that we were discussing so far. But if you look at it at the token level, individual token level, it is actually the cross entropy loss given the probability distribution over the vocabulary and the actual next token. So you'll actually be using PyTorch's cross entropy loss to implement this negative log likelihood concept that we discussed. So how you do it is basically every batch will have some training sequences. You will pass all the sequences in the batch through the model. So you will get a probability distribution at every time step of every sequence in the batch. You also know the targets at every time step of every sequence in the batch. You will be using the logits that you get and the targets to compute the cross entropy loss. And if you use reduction equals to mean, then you will end up getting the average cross entropy loss at a token level, which is the negative log likelihood at the token level. Why it will work for our purposes, that so far we were discussing negative log likelihood of the sequence, right? But all our training sequences would be of the same length. You will be implementing that. So it doesn't matter whether you take negative log likelihood of the sequence or negative log likelihood at the token level. So that is why you can just use cross entropy loss to compute the loss between your logits and your targets in the entire batch, and you will end up getting the negative log likelihood that you can use to implement the maximum likelihood estimation training process that we discussed in the previous slide.
Coming to the dataset in this homework, we will be using the Wikitext2 language modeling dataset, which has 579 articles, where each article has a different number of words. One of your first tasks would be to append and prepend SOS and EOS tokens that you have previously encountered. The dataset itself has the sentence sequences in the form of word IDs, which we decode using a separate vocabulary file that has also been provided to you. This vocabulary file has 33,728 items consisting of words, characters, and numbers. Taking a look at the code for the things we just discussed, we first load the dataset and the vocabulary files, which is stored as .npy files. We have defined and added the SOS tokens and the EOS tokens as a part of the vocabulary for you in advance. Additionally, it is highly recommended that you play around and interact with the dataset, print a few articles, and also print the first few samples from the validation set to get an idea of what you are working with. Unlike previous homeworks, instead of defining a custom dataset class, we will be defining our own data loader class that inherits functionality from PyTorch's inbuilt data loader class. Since our task is that of language modeling, where we predict the next token, our targets are the input sequences shifted forward by one time step to the right. Looking at the example here, if our article is I eat a banana and an apple every day, including today, for a sequence length of 3, a sample could be I eat a, and its corresponding target would be eat a banana. Now looking at the starter code, we first shuffle our dataset and calculate the number of batches based on the desired batch size, sequence length, both of which are hyperparameters for this task. In place of the getItem method in the custom dataset class definition, the data loader class uses the iter method to yield a tuple of the training input sequence and its corresponding target sequence in every iteration, with both the components being of shape batch size by sequence length. Custom data loader classes. Being able to create custom data loaders can be a very handy and powerful tool. It can help you go beyond simple batching by creating custom logic for constructing batches based on criteria such as data similarity or class balance. Consider using these if your data loading process involves complex logic, multiprocessing, or custom sampling strategies that the built in data loader can't handle. Additionally, this can help you enrich your datasets and improve model generalization by allowing for randomized transformations within a batch for increased variability. So you can consider using these when data augmentation needs to be tightly coupled with the data loading pipeline for efficiency or fine-grained control.
Okay, so far we've looked into how the data is set up, and now let's look at the code which is adapted from the starter notebook. If you would have looked at the starter notebook, you would be familiar with this code. So um, in the forward method, we will predict the next token based on a series of tokens that are taken in. So here we take in X, which is the context. So in the data loader, we just showed that X is the tokens, I eat, and then you would output a probability distribution that places an emphasis on the word right? So you take in X, and then you would also be taking in the hidden states for the LSTM cells that you're going to be dealing with. But if there is no hidden states, then you can initialize them. So X is the shape, which is batch size, comma time steps, right? Here, batch size means how many sentences are there. So in the example, we saw that there are two sentences or two sequences. So the batch size is 2 and the time steps is the sequence length, which is how many tokens are there in each entry in the batch. We also have an embedding layer to map these tokens to to an embedding state. So once we have the tokens in the embedding space, we then have the LSTM cells in which we update the hidden state of those LSTM cells, and then we keep generating new hidden states to make predictions. This is the language modeling part. So after the LSTM cells output a hidden state, we then use some sort of an embedding layer, but reversed, to map whatever embedding is back to the token space, right? So these are the three components of homework for part one. So the embedding layer is for mapping tokens into hidden states, and LSTM operates on the hidden states, and then the last layer, the token probabilities, map these tokens to hidden states back to the token space. So these are the three components of the model that we'll be referring to. Okay, so we take in the input in the shape, and then you feed it to the embedding layer that we talked about. And the reason why we initialize a list for the token probabilities is because we want to collect the hidden states for each time step. So if you have three tokens in the innate sequence, then you're also going to be predicting three tokens, right? You're not just going to predict the last time step. You're going to be predicting for all of those three tokens. So if you look at the data loader, if your input sequence is I eat you're not just going to predict banana, you're going to predict eat a banana, right? Because from I we predict eat, from eat we predict from we predict banana. So then if your input sequence has three words, then your output sequence should also have three words. So that's why we have a list. And then in the end, we would be returning the token probabilities list that corresponds to what your model thinks the next token is going to be for each time step. So for each time step, we get the embedding up to the current time step. And what we mean by this is that we're going to be predicting from the current time step. So back to the data loader. So we have three time steps here, right? We have three tokens in the sequence, which means we have three time steps. So for I, we select no context, or we could select the context I. That's because that's the only context we have. If you're on the second time step, we can select context equal to the first two words. And if you're on the third time step, we can select context that's equal to the first three words. So in each time step, we get the embedding of all the tokens up to the current time step. Now, we will feed the embedding through the LSTM cells that we have set up in the model in it, and then we will retrieve the final hidden state output. So we just feed the input embedding. So we just feed the input embedding and then the hidden state into the LSTM cell, and then we get a new hidden state. And then we feed into other LSTM cells, and eventually, when we are finished with the last LSTM cell, we take the final hidden state, and then we'll take the final hidden state and then feed it to token probabilities to map it back to the token probability distribution space. So as I said, LSTMs only operate on the hidden state space, and then you want to map it to the token space. So you can actually interpret it as a token, right? Because otherwise there's no way to interpret like a hidden state as a token. You can only do that after mapping. So these are the three things basically you do for each time step. You select appropriate context and you feed them through all LSTM cells, and then you map it to a token probability distribution. And then at each time step, you map the results for that time step to this list. And then in the end, you will just return that list. Okay, so coming to the RNN step, in the starter notebook, there's a function called as RNN step. So what this means is that since we have a lot of LSTM cells, we set this function up so that you can conveniently look through all of your LSTM cells at once. But then you can do it outside, but you can also do it outside of this function. It doesn't matter. So if you look at the starter notebook, we have made it very clear that we recommend you to use tosh.nn.lstm cell instead of tosh.nn.lstm. And the reason behind that is for homework for part two, your implementation for part one can be adapted to make your time at part two easier. And How you accomplish that is by changing your code from part one, but then that can only be done by using LSTM cell. If you continue using LSTM, then that would work for this. That will work for this homework, but it would not work for homework for part two. Okay, so if you look at the documentation for Tosha and n.lstm cell, then you'll notice that at each time step, it takes in two things. First is your input, which is going to be your hidden state, and the next thing is a tuple. Tuple consists of two things. The first thing is the hidden state of the cell itself, and the next thing is called the cell state, what's called a cell state of the cell itself. So the purpose of passing your input vector through each of the LSTM cells one by one is because you don't because you need more than just a loop. So you need a hidden state list. This list is going to keep track of all the latest hidden states for each cell. So that when you go to a particular cell, you can fetch the correct hidden state and then feed it to the cell with your input, so that when it gives you the output, it's the updated hidden state. You take the output and you store the updated hidden state to your hidden states list, so that you can also still invoke it. So this is what you do in the RNN step function. So you have your embedding, you feed it through all LSTM cells, but then you have to think about how you're going to manage those hidden states and cell states. And then in the end, and then in the end, you return these two things. So yeah. So let's talk about the predict function. So you have to complete the function predict, which is to predict the next token. This is very straightforward. You can read through them by yourself. It takes in an input of batch of sequences, and then it's going to output your model's guess as to what the next token might be. So the only thing to pay attention here is that the prediction function is actually it outputs a probability distribution. It doesn't output a single token. So the output is the probability score for every token from the vocabulary space. And the reason is that the only way we can calculate loss, because this is the only way we can calculate loss. Otherwise, if we just take the argmax, then there's no way for us to create the quality of the model, because we have to calculate the cross entropy loss based on the probability scores for each token. So this is the prediction function, and then we have the generation function. So the thing about these things is that as long as you understand the forward function, then all that is going to be easy. But if you don't understand the forward, then you're going to have a hard time. So please make sure you understand the forward function, and especially to understand RNN step.
So once your model has been fully trained, we could then treat it as a generative model and start sampling entire sequences of tokens. Now, your model currently can predict the next token, or more precisely, at each time step, your model will output the probability distribution of the next token. Now, like any other probability distribution, you can sample from it. And furthermore, we can sample entire sequences of tokens by following Bayes' rule down below, and by repeatedly sampling and feeding the sample tokens back into the model in an autoregressive manner. For this homework specifically, you'll be given partial sequences of tokens, and you want to extend them using your language model. Now, unlike what most of you guys are used to in LLMs, our generation doesn't stop when we reach a end of sequence token. Instead, the length of the extensions will be specified, and you simply just have to sample it n number of times as specified. You also have a choice of decoding strategy here. We've gone through a few of them in class. The strategy that will yield the most likely sequence is probably beam search. But for this homework specifically, you only have to implement greedy search. Now, lastly, to evaluate your generations, we'll be using OpenAI's LLMs. Now, LLMs have seen far more data than our language model has, and is able to more accurately model language. That means if we were to feed our generations to the LLM, the probability distributions outputted by the LLM will be far more accurate than our own. And so we can use those probability distributions to evaluate how likely or how natural our generations are. The specific metric we use is called perplexity, and it's defined as e raised to the average negative log likelihood of your entire sequence of tokens. Now, to pass the cutoff, you're going to have to reach under 1,400 perplexity. The code to evaluate your generations will all be included. You just have to paste in your OpenAI API key. Here's some pseudocode for the generation. You'll be filling this out in the notebook.
Training and regularization techniques. These are a few regularization methods that have been explained in greater detail in the write-up, and I would highly recommend you to read about all of them, even if you decide to use only one of them. You have explored log dropout in the previous homework, but it is a good idea to explore other methods suited for this task, such as embedding dropout and wait tying. Exploring the effects of wait initialization can also be a worthwhile experiment. Coming to general tips, unlike previous homework part 1s, this one requires you to run ablations to cross the singular cutoff of 5.3. Make sure that the validation NLL is sufficiently low, as we have observed a delta of 0.5 to 0.7 in the val and test scores on Autolab. This is particularly crucial because you will only have 5 submissions allowed on Autolab. Thus, it is recommended to set a target of around 4.6 for your val score and then attempt to submit on Autolab to check your performance after reaching sufficiently close to it. Lastly, the write-up is fairly long, but it is a great resource to learn about the different components of this homework and is definitely a worthwhile read. Thank you.